Good afternoon, everyone. It is my pleasure to welcome you to this new appointment of the 40 under 40 lecture series on combustion. Today we host Dr. Sven Eckart. He's a research associate at TU Bergakademie Freiberg Chair of Gas and Heat Technology. Since November 2022, he has managed several projects on CO2 neutral production and ammonia, methane, hydrogen, and their use in industrial processes as fuels. He currently leads the Combustion Technology Division and leads a large number of projects. His work has been published and presented at several international conferences. Sven has participated in several European projects, also his networking activities such as the EU Cost Action Smart Cuts Wire, and currently the Cypher Cost Action. He also received scholarships for his PhD from the EU and the state of Saxony, and is active member of the German VDI, the VGW, and the Combustion Institute. Today, Sven, we talk about blazing the trail, approaches to decarbonizing high-temperature industries. This is a topic I really look forward to hear about because it's also in our research interest. So thank you again, Sven, for having accepted this invitation. I give you the word for your presentation. Thanks.
Yeah, thanks a lot for introduction, and thanks again for making it possible to have me here. I am very pleasured about that. So title is already recommended. So we to talk about the decarbonization of the high temperature industry. Nowadays, maybe some words are allowed to tell you where is Freiberg. So here we can see Germany, a little more of Germany, and here in the eastern part we have state of Saxony, and Freiberg is here in between two large cities of Chemnitz and Dresden. So small town, but we have a university since 765, and picture of today, we have snow. So it's not very hot. Nevertheless, I would like to acknowledge the hot people from this picture. So our chair of gas and heat technology, led by Professor Krause, who's also my PhD supervisor. And as already said, I'm the head of the combustion group, and I would like to thank my team, which did a wonderful work in their projects, which make it possible to present some of the results today. Yeah. So also I would like to acknowledge all the partners we had in the 10 years I have been here at the chair. So universities all around the world, some scientific institutions which we have mostly located in Germany. And as you can see on the right part, a lot of industry partners which are directly partners in our research projects. That's why I hopefully can tell you something about the industry decarbonization. In the next slide, I want to introduce you to the topic of today. So if we have a view on Europe, here we can see the primary consumption in the year 2023 compared to the year 2005. So what we can see that overall, most of the countries achieved to decrease their overall primary consumption. So somehow in between 5 to 20%, in the middle, more close to 20% in the EU. Nevertheless, this energy consumption is in different parts of the industry. So we divide them in sectors, and here you can see them separated by each of the countries. And if we look a little more closer, industry, transport, residual, and also agriculture have in every country different portions of this sector consumption. So today, this is what we're looking into. We have the industry sector, which is different in many countries. So we're dealing with around 11 to 40% of the overall consumption in some of countries. So what are the industry that we're talking about? So which industry do we need to have to get carbon free? First of all, of course, metal industry have a very large consumption, very large production capacities, very high temperatures, up to normally in the range of 1,200, 1,300 degrees C. So they are emit around 8% in combination of the global CO2 emissions from steel, aluminium, and non-ferrous metals. Followed by, of course, cement. So both of them are also construction material. We need them in everyday life in every country, so they make a large emissions. Also, glass and ceramics are basic ware, which is for everyday wear, not only in industry cases, but also for personal use. And they sum up to around 1 or 2% of the global CO2 emissions. So overall, combined, we have around 17% of the world CO2 emissions, which come from these kind of industries. And we have not talked about paper production, textile production, food industry, and the energy production. So you can see there is a large facilities, large furnaces, large ovens, which deal with combustion in the most cases, which have a large CO2 emission. So nowadays, most of them are driven by fossil fuels. So what kind of methods do they have to get rid of this fossil fuel is first of all think about making it more efficient. So improving efficiency is quite a low-hanging fruit. Nevertheless, the companies have tried this for a long time. There are still some steps for improvement, like combined heat and power, also material substitution for their products, and of course, kind of recycling. For example, in glass industry, you can, if you use recycled glass crash and stuff like that, you can save a lot of energy compared to the new production of glass. Also, as we have talked in the combustion science field a lot about hydrogen, about the cracking gases, ammonia, and other fuels, which can be used for decarbonization. Nowadays, the industry is talking about this stuff too. They also talk about the electrical heating of their system. So DC heating, high voltage, microwaves, and plasma coming more and more into their vision, which could be scaled up also for their very power intensive systems. Accessibility to them, and maybe steps like DME and methanol if they want to get rid of oil. And what in the last 2 to 5 years also appeared quite a lot is if we have no access to kind of these fuels, there's always this goal of we could do CCS and CCU in combination with the other methods. So now today we will talk mostly about the hydrogen, but all of these others has to be considered as well. But hydrogen, in my perspective, is that one what is the most closest to the industry level nowadays. So if we look at the current projects which we have at the chair, we have investigated hydrogen ammonia since already 10 years for the combustion technology, but also the industry asked it for waste to energy and biomass to hydrogen projects, as well as a lot of electrification projects. In our case, mostly about microwave technology, but also laser and plasma heating technology and electrification to heat. So here I have a short overview about the projects in the last 5 years, and we started with some fundamental research on H2 combustion, how we can transfer our knowledge from the scientific point of view to the industrial point of view. So in Germany, we had a large lead technology study, which is called TT Goes H2, so thermal process industry is going in the direction of hydrogen, where we sum up all the fundamental knowledge that we have from the science-based sector, try to apply it to the combustion structure in the industrial sector, and including stuff like burner development, sensoring and sensors for safety issues, and also material. I will show you some results of this later. After this, or parallel to this, we started to looking into separate sectors. So we had partners in the glass industry, in metal processing, textile, additive manufacturing, and burner construction, which has their specific needs and questions. What is happening if we adapt or if we use hydrogen in our systems? And we have to solve these kind of questions which are related to the product quality. Because in the end, nobody cares what we heat. They want to have a temperature profile, and of course, they are mostly interested on the quality of their goods. And afterwards, there's a lot of projects dealing nowadays with bioheating and with electrification. So the variable energy sources coming more and more into play, because many of the players have seen that maybe hydrogen is not a step which we can adopt tomorrow. or in, let's say, the next 5 years. So in electrification is also something they have as a plan B in many cases. So in the end, we have a team of 33 researchers and PhDs, which are dealing with these topics and make a funding around 2 to 3 million per year with that. And in 80% of our projects, we have direct and indirect industry participants, so that we directly get some input about how is it helpful for them what we do as a research. Yeah. So as I already said, the highest requirements are set to CO2 reduction in the thermal process and combustion plants. So we think that hydrogen will play an important role. And mostly this is only true if we do it on a renewable basis. So we need some renewable energy first to have also a CO2 neutral fuel in the end. Afterwards, we're feeding this into the existing gas infrastructure for the storage and transportation reasons. So you maybe ask which grid. If we look on Europe, this is what the hydrogen backbone looks like. It has been the plan for the last 5 years, but this is the recent map about what is planned so far. And there are a lot of pipes which can be reused from the gas infrastructure here shown in, yeah, let's say blue or in green. And also there are a lot of pipelines that you can see here in yellow. They have to be newly constructed. So large 100 or some thousand kilometers have to be newly built. And also we connect to other continents to import and export hydrogen and further have some subgrid pipes. So what was the next plan for the industry to look into that? And this is a very German thing, der Gasnetzgebietstransformationsplan. This is really just one word to try to explain everything. It tells us how we can transform our nowadays natural gas grid into the direction of hydrogen to properly use them. And in Germany, this has been done since something like 10 years that they have as a plan to have partly the natural gas grid and transfer it to hydrogen grid. And this is what it looks nowadays in Germany. So this is the hydrogen backbone of Germany. And in the end, we have like 500,000 or 550,000 kilometers of natural gas grid, and in 10,000 of them should be transformed in a pure hydrogen grid. So the strategy behind that is to have the very large CO2 emission industries to get hydrogen as the first, so that we substitute just at some locations very large scale industry. And the DVGW did a large study in Germany to detect if the natural gas pipes can be used for hydrogen, and they found that 96% of all existing infrastructure could be used for hydrogen. So that is a quite large amount, and it make it possible that the lines that you can see here have been natural gas pipes before. Nevertheless, in some of the EEA states, they haven't any strategy or vision for 2050 and 2030 in some cases. But as you can see on Europe-wise, we have to think about a system which is connecting all of the countries. So we cannot have a regulation for one country which is not acceptable for the neighbor states, because this is also a thing we have to do in combination. So also standards sometimes are missing European-wide, which agreeing on how much hydrogen can be transported in a normal natural gas grid and what is the quality of pure hydrogen in the hydrogen backbone. In Germany, we have some technical rules, which is G260 and G262, which allow us to nearly go to 20% of hydrogen admixture, which in Germany is called the second gas family. And there is a fifth gas family, which is dealing with the pure hydrogen grid, and therefore there are different quality levels. So one of them is from 98% to 100%. The other one is very, very close to 100, it's 99.997%, which is normally what maybe electrolyzers need. And so if we have it in our gas grid, we have to deal with it afterwards. So how can we use it afterwards? Of course, combustion is what we look into that. And there we have some changes in the properties compared to natural gas. So we have a quite lower density, our calorific value is decreasing, but on the other side, the ignition limit and adiabatic temperature are increased with higher hydrogen content. So this conversion from natural gas to H2 requires that we have to look into the burner systems that we have nowadays in the market and look if we can optimize them or adapt them for hydrogen combustion. In the same step, we have the possibility to minimize pollutants in these combustion steps, as we have to revisit them anyway. And we can do a further increase in efficiency in this burner system for all of this. This requires a deep understanding of the methane and hydrogen combustion processes in any mixture situation. So which burners I'm talking about. So there are many, many different burners in the industry. So here I only pointed out some of them. We have some porous media burners, which are surface burners. We have some fan blowing burners, which can reach up to like 10 megawatts. We have some industrial burners with recuperating systems, which you can see, and regenerating systems. And some of these, they have like 10,000 burners of the same time in the market, and nobody wants to change all of them. So we have to think what we can do with the already existing infrastructure, because it has been quite costly to buy them. Also, furnaces that we have seen for the production, they are normally built for, let's say, 20 to 60 years in operation until they pay off for the invest. So nobody wants to change it every 10 years, because we have to plan to use hydrogen. Afterwards, we have to plan to use ammonia or something else. So the companies wants to know what they burn in like 20 years. And when they do an investment nowadays, they want to be sure that in this lifespans of like 60 years, if there is a transition to hydrogen, they know that they can adapt it. And they want to know this nowadays. So we in science have to be a little more close to the future than the industry is already. Yeah. So what were the large open questions that we were facing in the last 3 to 5 years? For the most cases, the industry asked, what is the change, or what is changing if we use hydrogen in our natural gas burners? So is it possible to just use the existing infrastructure, take hydrogen and burn it and see what is happening? And in the most cases, this was also combined with the regulation of nitrate oxides, as well as, of course, CO is no longer a problem, but about emissions. So pollutant emissions is controlled, and they have to be aware that they are inside of the limitations. So further, they wanted to know what is the effect of the changing in the flue gas composition on heat transfer, because in many processes we heat up some air or some flue gases, and they have to transfer a lot of heat to the product good or to water or whatever. So they wanted to know if they stay to the same efficiency or if they have to rethink their processes and maybe have to adapt their timings. So the influence on design and methods of the industrial burners and the thermal process plants was also a big question, combined always with it has to be safe. So they wanted to know what is happening in case of leakage, what is happening in case of materials, can they longer use it, and how to monitor flames. Further, they wanted to know what kind of materials is affected by hydrogen, how it is happening with condensation, for example, in their isolation material. So there are a lot of challenges that they were facing, and in most cases, they also talk about what is happening. If it's possible with hydrogen, can we also do ammonia? If we have it, can we do some low calorific gases, which we have as a waste stream? And what is about metals in the industry, and what can we do it electrical and hybrid heating as well? So a lot of combinations are possible, and we have to think about this. So in the most systems which are dealing with combustion, we have turbulent diffusion combustion in large industry play. So it's very complex very complex phenomena. So in the most case, for the scientific reasons, we have to simplify them. And if we want to investigate them, we have to go to much easier flames, which we normally do in science to understand and to validate our cases. So we have some validation data from the lab, which we then later use for a proper upscaling, both experimental and in the simulations. Further, we have also from the lab direct comparative values for different fuels, where we can say, okay, we have seen this in small scale. Let's see if it's happened in large scale the same way. Yeah, so this is the type of burners we want to look into. We need somehow a new design for them. So nowadays it's always a combination about experimental and simulations. And for the simulation step, we need some further data. So we have to know about geometry, because kind of the mixing of the fuel in the air in this kind of turbulent burners is key. For the emissions, we need to know how is ignition behaving in these mixing situations. We also have to know when our flame extinguish close to walls or material. We have to know what kind of emission we are dealing with, and if we have to use first stage or secondary stage to decrease these emissions. And one of the key parameters for me was always laminar burning velocity. So let's look a little more into detail here. And the first thing which is well known is that the heat value of hydrogen is lower than that of methane, which is the main component in natural gas. So we need nearly 3 times as much hydrogen volume based to get to the same power. And in industry case, it's only about power. Nobody cares about how many cubic meters reach the same temperature in the furnaces. So in the end, we transport 3 times more volume, so our geometry is not optimized for that in the existing infrastructure. On the same base, hydrogen needs less air for 1 cubic meter, but if we scale it up to power, it's only like 75 to 80% of what we have nowadays for air. So our airstream for the same power is getting reduced. So our old periphery equipment can be used, but the velocity of our airflow is decreasing instead of the fuel stream is increasing. So the mixing ratios therefore changing. And if we look on the global consumption or the global gas concentration in our exhaust gas, we can see here for 0 to 100% of hydrogen in our natural gas for power equal power systems. So if we add 40% of hydrogen in our natural gas, we have at the same power only like 15% of CO2 reduction. So let's see, this is a nonlinear trend, which you can see clearly here for all of the cases. And if we want to get to less CO2, we have to deal with very high amount of hydrogen. So that is why in the most systems, they thinking about one case of additional hydrogen in the natural gas for small quantities, and then the fuel switch to 100% of hydrogen to have this full potential of CO2 reduction. What you also can see is that we have an increase in water vapor concentration by 85% approximately in our exhaust gases. So this is something which is interacting with our material and product goods. So next step, let's look at the laminar burning velocity as one of the key parameters for reactivity. We again start with natural gas, which is something around 40 or 37 centimeters per second. So if we enrich with hydrogen until 50%, we have this kind of increase to around 60. So not even doubled. What you can also see here for stoichiometric case. But if we go to 100% of hydrogen, we go all the way up to here. So in industrial combustion systems, we normally use lean combustion, so we have a little more air than needed for our, but we're not running too much in the rich case. So for the normal industrial burners, we're dealing with here with around 7 times higher laminar burning velocity that we have. So we have a very more reactive gas than we have with natural gas. And this has impact in both cases, premixed and non-premixed cases, on the position of the flame. And with the position of the flame, also the temperature profiles are changing. And they are crucial for product quality. In some cases, in industrial furnace, over the whole furnace, we only have a variation in temperature about 5 Kelvin. So they are really much optimized for their processes. So this will have an impact on the industrial burners, which has to be checked. And further, I already said that in the pure hydrogen gas grid system, we have the possibility of 2% of gases which can be included. When we did this study in 2020, the discussion was if 5% is still acceptable. So we did some calculations for the laminar burning velocity with different gases which could be B as trace components in the natural gas, and saw that methane has the most crucial impact on the laminar burning velocity if we have 5% of change. Looking back to the slide before, this is 3% of change. So still with like 2 or 3% of trace components, we have the same effect which we have here with 50% of hydrogen enrichment. So pure hydrogen is very sensitive to trace components. If we look further on a typical gas standard, which is the Wobber number, which is kind of a number which tells you if a gas is interchangeable or if a burner which has run on natural gas before is accepting another kind of gas mixture. Because natural gas has very much deviation in their concentration, so there is a low calorific natural gas and there's a high calorific natural gas, and they have different calorific values. Hydrogen has a much lower calorific values, as we already have mentioned, but depending on these 2% of trace components, it's also very much changing in the Wobber numbers. So the regulations that we have nowadays tell us that it's not really much interchangeable between natural gas and hydrogen. So we have kind of to redevelop the burners from these kind of experience. Also, in many cases, industrial burners deal with some strategy to mitigate NOx concentrations, and some of them are, for example, exhaust gas recirculation or air staging. And in this kind of cases, we have a variating of oxygen content. So we wanted to know how this is affected by hydrogen enrichment, and did an experimental study on the laminar burning velocity, where we added different portions of hydrogen until 20% and decreased the oxygen content to around 14%. So dealing with a rich quench lean situation or an exhaust gas recirculation. And afterwards, we tested 11 detailed reaction mechanisms to see if of the laminar burning velocities in the rich and the lean case. This was done together with colleagues from Budapest, Tamas Turani's group, and they have done the simulation and afterwards developed a graph which can show to the scientists in the industry which of the mechanisms is very suitable for these kind of situations. So in this kind, overall, the Glauberg mechanism and the Caltech mechanism, they could predict about 80% of all experimental data that we did in this study. So they were quite good. But we found all out that not all mechanisms dealing equally good on the lean and the rich side. And in the case that we want to combine or calculate the effects of staged combustion or exhaust gas recirculations, we maybe have to combine some of these mechanisms for a proper pre-calculation of these experimental setups, and also to later use it in CFD of large-scale simulations, because there normally we cannot use detailed reaction mechanisms due to the size of all our systems. So the next step that we took into account is the extinction of these kind of flames. So we investigated in a non-premixed counterflow burner, which is also quite an easy setup. And there we as a Hasses group, and they did the simulation for our experiments to show if we have a second value where we can predict the behavior of our flame with an hydrogen enrichment. Also here, it was key that we wanted to see what is happening if we reduce our oxygen content. It was shown that the extinction strain rate is a very useful parameter for the mechanism development and to predict the hydrogen extinction, which is of course extinguished much later as to the high reactivity of hydrogen. But there are different mechanisms which can predict this value good and compared to the laminar burning velocity. So it would be a proper to say that both should be used as a validation case if we want to pick a proper numerical setup. Yeah, from that step, we went back to our premixed heat flux burner and measured the NOx concentrations. And as in the industry, we wanted to see if they are true with hydrogen is producing more NOx. So we did some studies and normalized on the residuum time and also on the exhaust gas concentration, and figured out that in the case where we have our industrial burners, purely because we have more hydrogen enrichment, we're dealing with around 40% more NOx production. So this has to be checked also if it's true from our premix burners in the large scale turbulent burners as well. So that was the fundamental step that we could give the industry like 5 years back, which were the experiments in our lab. And then afterwards, we started with this large lead technology project where we get directly to the industry. We have picked 6 industry partners from Germany and over 60 companies which are working with us in 3 project parts. The first one was looking into the emission of the combustion systems with 0 to 100% of hydrogen, divided in 2 cases, enrichment until 35% of hydrogen and the 100% case. Then we had a second project which was dealing with combustion control, so they were more about the flame signals and the safety issues. And we had a third project which were dealing about the effects of hydrogen combustion on our combustion products and on the material in the furnace itself. So I want to show you some results from that. So we took 3 burner systems which are widely used in the industry: a cold gas staged burner from the company of Honeywell, a fan assisted burner until 0.5 megawatt from Weishaupt, and there's also a VS recuperator burner which was used for flux combustion, which or mild combustion. Yeah, so 3 different research facilities, all of them having some large scale testing equipment where we could test the burners on different ways. And I will start with the combustion of the staged burner from Honeywell. Shortly introducing our experimental setup. So we have a large scale combustion chamber, which is around 5 meters long. We have multiple stages, so each of these models can be changed with each other, so that we have the possibility of having a wall heated model. We have a one model which can resist up to 1600 degrees C, and we have also the possibility to do some exhaust gas recirculation in the burner itself and in this model, in this segment B. Also, they have optical access from all the sides, so that we can introduce laser sheets from the horizontal part and have a look from the top part. Further, we of course have some thermocouples type S to measure the flame volumetric and for the radius, and we have access for thermoacoustics, pressure regulation, and all of these stuff. So here we put in our burner in a burner stone, which is movable in the axial direction. So we have the possibility to see each part of the flame through the top windows there. And from the fuel side, we have the possibility to add 6 components: CO, CO2, hydrogen, nitrogen, methane, and oxygen if needed. If we want to have maybe a biogas or a synthetic natural gas or an industry gas. And we have also oxidation from 0 to 100% of oxygen enrichment in the air. And the largest capability that we have is normally 50 kilowatts with our exchangeable burner. So this is what the burner of Honeywell looks like if we put it on our chamber, and how the chamber is looking like through one of the laser ports if we reach like 1200 degree inside of the chamber. This is what normally a natural gas flame looks like. So we have a typical industrial flame, which is lightly blue burning from a burner nozzle, which has the size of around 5 to 10 centimeters. And if we then enrich until 100% of hydrogen, we easily can see there is something changing in the luminescence. So in the case of 100% hydrogen, we have kind of a reddish flame. This is even changing after 50%. And after 75%, at this time, we realized, okay, seems that our flame is extinguishing later. We have some glowing effects in our burner structure, which is not normally the case for natural gas. So that was the first kind of easy indicator that we have to change something in our burner system. And together with the manufacturer, we went to the mixing plate, which you can see here. This is the old mixing plate for natural gas. This is the new one for hydrogen. And the main case was to get to the same flame shape as we had before. So we did some changing in the mixing concepts, reaching a flame which looks equally to what we have as a natural gas flame, which we could investigate a little more in detail about the UV, vis, and temperature and emission profiles for all of the enrichment behaviors. In the end, we have two different mixing cones. One is good for the enrichment from 0 to 50%, and the other one is optimized for the hydrogen case. Nevertheless, the hydrogen mixing place is not longer usable for natural gas, which you can see here. So the mixing is not properly, and we have a very flat flame in our furnace, which is normally not acceptable in the furnace. So until now, we not have a mixing cone which can operate from 0 to 100%. But in the case that the company wants to use their already adapted burner, they just have to switch this little mixing plate and they can fully operate on hydrogen, which is, I think, a good step. Also, we have tested about the concept for NOx mitigation, and therefore, in this kind of burners, mostly air staging is a concept which have been used. Here you can see the emissions of NOx when we have no air staging at an equivalence, at the lambda, which is the opposite of occurrence ratio of 1.1. And all of these other cases are with air staging. And in any of these cases, in all of these cases, we have less NOx emissions than we had with an unstaged system. Further, it was shown that with the new plate, we can also reduce, or with an optimized version of the new plate, we can also further reduce 10% of the NOx emissions that we had for pure hydrogen, still having in all cases more NOx emissions than we have for the pure natural gas flame. So what we have seen in small scale flames was exactly the same what we saw in large scale flames. Nevertheless, now we have trends and we can work on more optimized burners and more optimized mixing concepts to further reduce the NOx concentrations. So to sum up the results that we have found, for 20% of hydrogen at mixture, they have not find any effects on the material in the burners, and we have not really much found any flame dimension changes, and also all of our gas supply structure is adequately dimensioned, so we can still use our existing systems for 20% of enrichment. Also, flame monitoring is working very fine. If we go to 100% of hydrogen, in the case of gas family 5, we see a flame shortening and also an energy density increasement and an increase of the flame temperature in the furnace itself. And therefore, we have to adapt kind of our burner. So we have to make sure that we have a proper wall cooling for our burner system or use different materials. And we have seen that this effect can cause damage in our burner itself, and found also that we have a moderate increase in NOx emissions. Also, the flame monitoring has to be changed to ultraviolet sensors, as ionization sensors are not working properly in the case of 100% of hydrogen. So there were some strategy that we have tested. So if I already said, the increase of the airflow and the mixing concept has to be changed for these type of burners, and we have to revisit the others as well if we want to go to 100% of hydrogen. Further, we have to adapt the NO mitigation strategy as mild combustion stage, switch quench lean, and EGR to see if we can reach the same reduction quantities that we have for natural gas. In some parts, we have to have change. For example, mild combustion cannot be operated at the same recirculation rate that we had in natural gas cases. Further, we had also requested or talked to other scientific partners and industry partners that the NOx measurement and the limits should maybe change to milligram per kilowatt hour or to milligram per ton production good, to make it more comparable between these two fuels, as we have a much higher water vapor content. So as I have not too much time, I will maybe only shorten present this part. We have done some aging tests for 600 hours in different atmosphere from natural gas to hydrogen to see how our refractory material is affected. Here you can see two typical refractory materials, and we have not seen too many changes in them. If we look on the metallic samples, after 600 hours, we have seen a clear oxidation. So there are some changings in the oxidation states of some of these metal probes, and they have different effects in natural gas and hydrogen. This has to be investigated for each of these materials separately, so we cannot have a conclusion for all metals at the same time. To make it short, for the ceramic structures for aluminium oxide, there was not a clear influence. For silicate oxide, for silicium oxide, we have seen a higher mass loss in already 600 hours. So it could be that they degrading faster as experienced. And for silicium carbide layers, we had a strong oxidation, which also is investigated in a further project. And for the metallics itself, we have seen stronger corrosions in some cases. In other cases, we haven't found them. Then we have no clear dependency for some cases in the damage various. So chromium and aluminum content play a certain role in the oxidation processes and sometimes changing their behavior from 0 to 100% of hydrogen combustion atmosphere. Also, in nickel-based materials, they tend to be more resistant to hydrogen combustion than the other materials which we have tested. All in all, we scanned around 23 of them. So this was the step for air combustion, but in some cases we have to go to much higher temperatures. And one of the projects I want to show you a little more in detail is combustion in the glass industry. Therefore, we have worked together with Schott and the GWE in Germany to see how we can decarbonize the glass melting industry and avoid CO2 emissions by having hydrogen oxyfuel as well as microwave boosters, and test some alternative raw materials to improve the CO2 balance. So what we have talked, or what I have talked about in the last minutes, is going from natural gas as a reference case to air hydrogen combustion. In this case, we could reduce CO2 to nearly 100%. We can also use natural gas and go to oxyfuel combustion, which means just pure oxygen as the oxidizer. In this case, we would have a fuel savings, so also more efficient system, because we don't have to heat up our nitrogen. And nowadays, we tend to do both. We want to reduce CO2 by 100%. On the other way, we want to get rid of the N components in our gas and go purely to hydrogen and oxygen. So in a perfect 100 case, we would have 100% of water vapor as an exhaust gas. Yeah, this is what we did in 2021 with very small premixed flames in the lab. So changed them from natural gas to hydrogen. Then we scaled this up to 3 burner types, which are operating at 50 kilowatts, then of course in a non-premixed state. So if we look back on this table, there are some difficulties coming with the 100% hydrogen oxygen case. We have very high temperature reaching 3000 Kelvin, so it's very difficult to measure. Mostly in the lab we would use laser-based methods, but in large scale we have not the optical access for that. We have problems with the emission because we reaching up to 100% of water vapor in the exhaust gas, so most of the analyzers are not possible to measure at these extreme conditions. The extinction is we expecting much more stable flames, so we not even had the chance to do some proper experimentals in our model burners. And at the last, we have very high burning velocity, so we're reaching about 9 to 10 meters per second. So there's only a few data in the literature. Some of them is unreliable, some of them is out to date. So from all what we have discussed in the last years about hydrogen air combustion, we also know the phenomenon of cellularities in H2 flames. So there are which has to be dealt. So first of all, we went to these small premixed flame burners, and there are two kind of burners. One of them is a one-hole burner, which is normally operated to cut glass, and the other one is a line burner, which is heating up for the forming process. For example, if we have a glass pipe, and they want to make little flasks out of that for the medical use or the pharmaceutic use, they use kind of 100s of these burners in a production line. So what we wanted to do is to switch them from natural gas to 100% of hydrogen, and this was not possible with the existing geometry. So at small powers where they were operating, we had a lot of problems with the flame flashing back. So we have to install flame arresters as all other systems, and we also found a slight increase renew their production line. So also this comes with a change of the flame position, and there, what we else find is that the thermal radiation from the flame was increasing with was decreasing with increasing hydrogen content. So as I had said, we had some problems with stabilizing, getting too close to the burner, and the burner starts glowing and heating up, and at a certain time we have flashback situation, even with this pilot one hole burner. And in the case of a multi-line multi-hole burner, some of the flames flashed back, and we had a full flashback of the combustion system. So this is not acceptable for a production process where they operate this burner 24/7. Yeah, then we scaled it up. Here, in this case, I want to show you some flames of 20 kilowatts close to stoichiometry, and we expected to go from 0% to 100% of hydrogen oxy-fuel combustion, but you can clearly see that there is some changes in the flame. In the glass industry, there is no flame detection, as they have always very high temperature with self-igniting. But for other industrial processes like steel making, they operating with a flame sensor, and it was possible to use the normal UV sensors until 100% of hydrogen for these. So what we could see is a significant change in the luminescence of the flame, also a change in the white of the flame base, which you can see here up to 100% of hydrogen. And the flame height in the free combustion system, it's so we wanted to see if this is also the case in the furnace. So we put the burners in our combustion chamber, as I have explained before. So here we have this turbulent nozzle mixing combustion, and we did flame pictures for each of these scenarios for 100 times and recombined them afterwards. What you can clearly see that is with an increase of the hydrogen and mixture, we have not really much a change in the flame length. So the flame length is nearly the same, only the width of the flame is increasing. What we also can see is the concentration of OH radicals was increasing, but not too much critical change in the flame overall with the hydrogen and mixture. So in the end, we had no design adjustments to be done with the already existing burner infrastructure, which is a good thing for the industry because it's cheap. We also wanted to know what is happening if we have nitrogen in our system, because in the lab we can use pure oxygen, but in industry case where we have very, very large furnaces, they don't use 100% pure oxygen. They use air separation units, and depending on how they use them, there are still some parts of nitrogen in the oxygen they use. So the quality can be different. And we tested from 0 to 7% of nitrogen increasement in our burners, and saw a significant increase of nitrogen oxides depending on the hydrogen ratio. This is always for a dry gas combinations. So depending on the only slightly higher combustion temperature in the oxy-fuel combustion, so it's only 25 Kelvin difference, we had an increase of the hydrogen very much for. So we have to care about false air and the quality of our oxidizer. So in the end, for the hydrogen admixture in the oxy-fuel burners, we could reach a stabilization of the flame for all burners. In the premixed case, up to 100%. In the non-premixed case, until 100%. We could measure the temperature profiles, which are very crucial for the production. And we can also measure the OH concentration, because in a kind of glass melting situation, OH can interact with the reactions in the glass and maybe change we have less heat radiation from the hydrogen flame, which is normally not a problem in the glass melting process, as normally the roof of the glass furnace is radiating to heat the glass equally. So the flame is not what is giving the radiation. And we found that the oxidizer quality is crucial for low NOx emissions. In the project, we also material process and steel industry, they are available. And to conclude these, there is a lot of knowledge which has already been transferred to large scale and industrial processes. We currently have research projects about glass, metallurgy, magnesium, steel. Not found any showstopper in the process. So still there are challenges remaining in many of our projects. The renewable generation of hydrogen is key. So after this project, as we know, everything would working fine if we would have hydrogen, but still there is no renewable hydrogen which we can use in this large amounts. There are still safety concerns in the industry and the populations for hydrogen, and of course ammonia as well in the future. And the product quality is key for them. So after adapting the burners and having different flue gas and everything, we have to have the same product quality. And a last step, which is not really much understood, or which we need to clarify more, is the material interaction with oxy-fuel atmosphere as well as hydrogen air atmosphere. So full takeaway messages, and I quote Professor Hasse, there was never been a more important time to be an energy engineer. We need to speed up with transferring our knowledge to the industry. From the basic research we do, we have to tell them what could be a proper way, and saving the energy. So first thinking about efficiency is much better than have to substitute it afterwards. And when we have to substitute it, it is necessary to focus on multidisciplinary approaches, because we have to care about the acceptance in not only in the industry, but also in the economic stake and the politics, that we're not running into a problem here. Yeah, thank you for your attention.
Thank you very much, Sven, for this very nice talk. We have time for questions. So if anyone in the room, in the virtual room, has questions, of course, you can raise your hand and ask it directly, or if you prefer, I can read your question in the chat. I will start with the question myself so that everyone warms up a little bit. I had one question about your view on this point. So when we talk about these regimes like mass combustion that are actually, we say, fuel flexible, indeed they are, but when you change completely fuel, I don't know, if you go from methane to hydrogen, full hydrogen charge, we do realize, and I think you also showed to some extent, that the topology of the flame changes significantly, and then of course the combustion process is not the same, with consequences with I don't know, NOx emission and other things. And so would it be more appropriate to say that there is some property, I don't know, the Ancoller number, that should be constant in order for the combustion process to be always mild, I don't know, what is your point of view on this? Because I saw that you actually, in a way, you go in this direction by changing the design of the injector, which means that you actually consider the differences in the chemical reactivity of the fuel on the subsequent or the final, let's say, structure of the flame and the characteristics of the system.
Yeah. First of all, we are not the mild experts. We have
Okay, but
industrial burners from WS until 500 kilowatts, which could be mild. In this case, it was regenerator burners, but we also have recuperator burners, and we changed them for the melting of magnesium. So in the end, it doesn't have very much contact to the product, just to change the furnace. And we have tested them in a furnace which is 5 meters long, 3 meters high, something like that. What we found is that after around 70% of enrichment, it was not possible to go in full mild stage, so not fluxing anymore. We had some parts in the furnace where we still had a flame. It was very wide lifted, so in the range of like 1 meter, 1 or 2 meters, there was only a very small flame, but the NOxes increased very rapidly when we have this kind of stabilized flames, even very large in the furnace or with a large distance in the furnace. So there is something where we told the manufacturer that we have to look into that to get a more proper mixing in this furnaces as well. For natural gas, it was very easy. We have never been a problem with this mild, but for hydrogen, in some cases, we have a lifted flame and a mild step to this flame. So, of course, there have to be some adaptation, but we have not done this until now.
Thank you very much. Madi, you had a question, right? Madi?
Yes. Thank you for your presentation. I have just one genuine curiosity. Maybe probably there's no explanation behind it, but in slide 44, if I'm not mistaken, you were showing the temperature evolution as a function of the hydrogen enrichment, like from 0 to 100%, if I'm not mistaken. Yeah, and there is from 0% to 20%, there is a dip at 20% in the temperature, and then it starts rising up. I was wondering if there was any kind of explanation, in flame behavior, or if you had done any I don't know, CFD to see that why there is this dip. Sometimes also from my experience, because I also work with pure hydrogen, there are some trends even in the emission or in the chemiluminescence or in the temperature that cannot be really explained well why it's actually happening. So I was wondering if you had also this problem as well to explain it, why it's going down and then coming up.
Let's say in large scale, we have not the good old stabilized conditions that we have in a lab. So sometimes, or for temperature, it's very much depending on the furnace temperature, wall temperatures, and heat radiation into the flame back again, which sometimes can cause problems if you run such a test setup. Or in our case, we heat up our combustion chamber for 2 days, and then we can do 3 days of testing 24/7. So we have a temperature fluctuation sometimes around 50 Kelvin in the chamber, which can cause also higher temperature in our flame measurements. So correcting radiation effects on thermocouples, for example, is a very key point where you can have some slightly changes depending on how you do that. But we also saw some kind of flames where we had unexpected phenomena that they have the highest temperature for 80% and then decrease to 100%. In some cases, we could, by imaging these flames in the ultraviolet, so OH radical chemiluminescence, we could see that the change in the flame position to the point of measurement is sometimes the case, so that the flame getting shorter and at the same time we measure at the same location, so that we have a different resistance time or stuff like that. In the lab scale experiments, we normally have trends which are very good explainable. But for larger turbulent flames, we sometimes have a larger deviation than we know from the lab.
Right. Thank you very much. Much appreciated.
You're welcome.
Any other question?
I have a question. On one of the plots, you showed the laminar flame speed against hydrogen enrichment, and up to 50% hydrogen enrichment, that trend is pretty much linear, and beyond that, we see an exponential rise. And there's a similar behavior with respect to NOx emission as well. And so I was just wondering, at what percentage of hydrogen enrichment does it become essentially important to study the effect of preferential or differential diffusion, and how much of a role does it play towards thermodiffusive instabilities, which then translate, of course, into NOx emissions as well?
Yeah, very good question. I can give you not a percentage, to be honest. We found in the most combustion systems that after like 70%, we have a clear change in many properties. This could also be shown in acoustics. This could also be shown in heat transfer. So we mostly define this as the hydrogen dominated area or something like that. So 0 to 50% is kind of methane dominated. Then we have this transition state, and after 70, 75%, it is more like hydrogen dominated. So I would say this is maybe the area we have to look a little more into detail. Nevertheless, from an industry perspective, this is also the less important area, because nobody will increase the natural gas grid to 70% of hydrogen. They will always go to 100%. So this is a part which is maybe of scientific interest, but for the industry, they mostly don't care about that.
Yeah, thank you very much.
Thank you, Mustafa. I don't know if there are is another question from the audience. Otherwise, I'd like to thank you again, Sven, very much for your talk and for your presentation. And I would like to thank everyone else for attending, and wish everyone a good weekend, and see you next time for the next episode. Bye-bye.
Thanks very much.
Ciao. Bye.